All right. Let's start talking about rotational energy. Okay. Um, we know that if objects rotate, if an object rotates, it has what's called rotational kinetic energy, which is a different type of kinetic energy, and we can get that equation with K sub r is equal to 1/2 I omega squared. Okay. And that's compared to the translational kinetic energy, which you know is 1/2 mv squared. Okay, so they're all the same, right? But we're just turning m and v into the rotational versions. Okay. When you find the gravitational potential energy of an object, we always measure the height with respect to the center of mass of the object. Okay. Okay. So really quickly, okay. A heavy block of this is called a physical pendulum. A physical pendulum is like a rigid body that oscillates that swings like a pendulum. So maybe something kind of like if you took like a wooden spoon or something. That's one of the best examples I can think of. A wooden spoon, and you held it about some axis, and you gave it, you let it lift, and it would oscillate like a pendulum. Okay, or it could, right? Well, that's called a physical pendulum. Okay. Um, a heavy block of mass 3 kilograms is attached to a rod, also of mass m, and length L equals 2 meters. The end of the rod is not attached to the block, or the end of the rod not attached to the block is pivoted on an axis to form a physical pendulum. The assembly is displaced in angle theta equals 37 degrees relative to the vertical and release. Determine the speed of the block as the assembly passes through the vertical. Okay, so what you will notice, okay, is that we actually have to solve the rotational energy. We actually will have to use energy for both objects. We're going to treat the rod separately from the block, okay? The rod's center of mass is going to be right about dead center right there on the rod, and the block center of mass is also dead center. Well, notice that when it initially starts out, you can kind of see the shadow of it here. Initially, the center of mass is right there, okay? And initially the center of mass is right there, okay? So you can see, right, this is us just showing, right, where the center of mass was and where it is now, okay? Um, it's important to note a couple of things here. The first thing is that we need to be able to convert from, initially when it's held like this, it initially has gravitational potential energy, and it turns into rotational kinetic energy. Okay, it turns into rotational kinetic energy because what's going to happen is this is going to swing and it's going to rotate in a way. Okay, so the first step that I need to take here, okay, is to get the moment of inertia of the object, the combined object. And in order for me to get the moment of inertia of the object, I need to get the moment of inertia of the block and add it to the moment of inertia of the rod. Okay. So I'm going to take the moment of inertia of the block, which is going to be mr squared or ml squared. The reason is because this is going to be treated as a point mass at a distance L from the axis of rotation. Okay, so I'm going to call this ml squared. Okay, the rod is a rod pivoted about one end, and the moment of inertia, which would normally be given to you, is 1/3 ml squared. 1/3 ml squared. Okay. ml squared. Okay. When you add that together, you end up getting 4/3 ml squared. Okay. And that will then, we can plug in our numbers and actually figure out what this will end up being. So 4/3, the mass is 3, L is 2, okay, squared, and we can figure then out what it ends up being. It ends up being about 16 kilograms times meters squared, okay? Okay, so there's that, all right. Okay, now I need to figure out the second thing I need to figure out is delta y of the rod, okay? Well, that's the hard part, is I need to figure out the change in height of the rod, okay? Um, and the way that I was able to solve this, and it's kind of weird, okay, is that if you notice that this technically makes a triangle, okay, this technically is making a triangle, and what I need to do is if I've got the rod length L right here as my hypotenuse, this is my um, angle, okay, theta. Then what I can do is I can actually use my trig identities to figure out um, what the height change ends up being. And I think this actually might be also something that's taught in simple harmonic motion as well, okay? But you can see that I can actually figure out the height. And you'll notice that whatever I figure out the height to be, okay, this top height right here is going to be 1/2 of that height. This is just going to be the full height, okay? And I actually end up finding out you would use your trig, you'd use some trig identities here to figure this out, but you can actually figure out that the height is going to be equal to, or sorry, height h is going to be equal to L times 1 minus cosine theta, okay? Okay, so when you do that, okay, you would get delta y equals 1/2 L times 1 minus cosine theta, okay? That's specifically of the rod, okay? Okay. And then you'd have to actually substitute everything in now, okay? You get 1/2, L is 2, and then 1 minus cosine theta, which is 0.8. And you should notice that these are going to cancel out, and so you're left with 1 minus 0.8. So delta y is just 0.2 meters, okay? If I figure out delta y of the block, it's not much different, okay? Delta y of the block is not much. I mean, we already said this is 1/2 of h, so 2 times that would be 0.4 meters. Okay, it falls 0.4 meters as it goes. Okay. Okay. And then now what I got to do is I got to do conservation of energy. Okay. Conservation of energy. Okay. When I do conservation of energy, okay, I'm just doing the mass of the rod, okay, times g times delta y of the rod, okay, plus mass of the block, plus times g times delta y of the block, okay, because both initially have gravitational potential energy, and it's all going to get turned into rotational energy, which will be the same for both, okay. And now I can just plug everything in. I've actually got all these values, so I can just plug everything in and figure out what omega is going to be, okay. So when I do that, the mass of the rod is 3, g is 10, delta y of the rod is 0.2, plus the mass of the block is 3, g is 10, delta y of the block is 0.4, equals 1/2. The moment of inertia we already figured out was 16, and then you get omega squared, okay? And then you actually have to multiply all the stuff out, and you'll and figure out what it should end up being. The whole left-hand side ends up being 18, okay? So this ends up being 18 equals half of 16 is 8 omega squared, and you end up seeing that omega is equal to 1.5 rad per second, okay? Now, that's great. That's awesome, okay? Here's the thing. That's not what we're asked to find. We're asked to find the speed of the block, okay? And when it says speed, we're talking linear or translational speed, okay? Not rotational speed, okay? So when I'm talking about linear speed, I now need to convert to v, okay? And in doing so, okay, that's going to be v equals omega times r, okay, and that's going to be 1.5 times radius, which is 2, and that gives me 3 meters per second, okay, and that ends up being the speed, okay. All right, that is rotational energy, okay, so we'll be back next time with rolling objects.